Hello everyone, my name is James Baxter. I'm the current president of the Autonomous Robotics Club of Purdue. We're a primarily undergraduate student club at Purdue University looking to grow the skills and abilities of our members through hands-on design projects centered around advanced autonomous robotic systems. I'm here to introduce our new onboarding resources first developed in the fall of 2020. These resources are targeted for new members and assume you have some baseline knowledge of programming. They're self-paced and include links to external resources that can explain some concepts and tools in more detail than we do. It's designed to run on any modern computer, allowing you to learn safely from home. The first part of the tutorial is installing some software, which I'll talk about at the end. Afterwards, you can get started on the fun part, using Robot Operating System, an industry-standard tool to program robots, to build a controller for a robot playing the classic snake game. This takes place in a simulation environment that I built in Python, but the workflow is essentially the same for the physical robots you'll interact with through the club. Let's take a look at Google's implementation of the snake game to familiarize everyone. Simply Google snake game to bring it up, then hit play. The snake is moving in a 2D, boxed-in, horizontal field, trying to eat apples. Each apple adds an additional segment to the snake's length and increases the score. This also increases the danger, as the snake will die from running into its own tail or from hitting a wall. This is the basic concept of the game you'll design a robot to beat. Let's switch gears and look at my implementation of the snake game. I made some modifications to make it more similar to a real robot. The first thing you'll notice, after the graphics maybe, is the snake's heading is continuously variable, meaning it can point in any direction. You also control the angular velocity, meaning the rate at which the heading changes, rather than the heading directly. This is similar to a real robot using differential drive. Think of tank treads, or a robot with a wheel on each side and a caster wheel in the back. I'm now going to load up what you'll have created by the end of the onboarding tutorial. I'm not giving any controls to the computer, and it is operating fully autonomously. It receives the location of itself and the apple, then through several layers of logic determines the proper control signal to send to the simulated robot. A more complex simulation would include processing raw sensor data to determine these locations, but this is left out in order to simplify the tutorial. As you can see, the robot's logic is fairly simple and it will eventually fail. If you want, use this as an open-ended challenge to create a better system and dive deeper into the concepts introduced. Now that you've seen the project, let's quickly talk about the software and how it's running. The first thing you'll install is Docker, a lightweight virtualization tool that allows you to run our customized Ubuntu container on any operating system. On Windows, this also requires WSL2, Windows Subsystem for Linux. This is a full Linux kernel running alongside Windows. In our container, we have ROS installed. That's the robot operating system I mentioned earlier. This is an industry-standard tool for creating autonomous robots, and it has an API for both C++ and Python. In this tutorial, and for most club purposes, we'll be using Python, since it's a little bit easier to get up and running. You'll also gain experience with using Git and Bash, which are essential for working in industry. This concludes the introduction to the onboarding resources. Check the description for more information on how to get started. I hope you enjoy the tutorial and your time in ARC.